Although it's useful to have it for an alternative integration procedure, the parallel axis theorem is more useful in evaluating area moments for cross-sections that can be represented as a superposition of simple shapes. We previously used it to generate expressions for Ix and Iy of an I-beam. It isn't always the case, however, that we can see by inspection the location of a shaped centroid. This U-shaped cross-section is symmetric about a vertical axis bisecting its base, so we know that for a cross-section positioned at the center of the base, x bar is 0. We don't yet know the value of y bar in this coordinate system. We want to first find the centroid, then find the area moments of the cross-section about a coordinate system positioned at the shaped centroid. In problems like this, we need to pick a coordinate system somewhere to start with. And because of the symmetry of this object, we'll position this coordinate system so that its origin is right at the bottom center of this horizontal member of the U section. We'll divide this up into 3 rectangular segments and call them 1, 2, and 3. The centers of the rectangles will be right in their middles, which we'll indicate by these red X's. For area 1, its centroid is half its height, or 6 millimeters, and the area of 1 is 4 by 12 millimeters, or 48 millimeters squared. Area 2 is going to be very similar. It's going to have the same Y centroid at 6 millimeters and the same area of 48 millimeters squared. For the third area, its center is at 2 millimeters, and its area is 24 by 4, or 96 millimeters squared. The centroid for the whole object, then, is just the area-weighted average of the centroids of the constituents. So we could write it this way. And since y1 bar and y2 bar are the same and a1 and a2 are the same, I'll write that as 2 times y1 bar times a1 plus y3 bar times a3 over the sum of those areas, which is 192 millimeters squared, and that number turns out to be 4 millimeters. And that tells us the centroid of the whole shape is right here at the top center of that horizontal member. So the coordinate system we're going to use for solving for area moments is the one that we have in blue here. This is our centroidal coordinate system for this cross-section. One of the things we can see here is the differences between the local x and y axes for each of the constituents and the x and y axis for the whole system. So what we'll notice is that the distance between parallel x-axes in all of these cases is actually 2 millimeters. We've got for areas 1 and 2, 6 minus 4 is 2, and for area 3 we've got 4 minus 2 is 2. So for calculating Ix, the quantity dx will be 2 millimeters in all cases. For calculating Iy, we have for areas 1 and 2 a sum which is half the width of the vertical members plus half the width of the horizontal member, so that's going to be 2 plus 12, or 14 millimeters, is going to be the dy for areas 1 and 2 for calculating Iy. The local y-axis of area 3 is coincident with the y-axis of the centroid of the shape, so there will be no parallel axis contribution for that. So now we can write down the area moments about the x and y axes of the centroid of the shape. The contributions from each vertical part of U will be the same, so we'll have 2 times a BH cubed over 12. All the dimensions will be in millimeters, so we'll leave those off. 4 times 12 cubed over 12. And then again, the parallel axis offset is 2 millimeters, so this is plus the area, which is 48 millimeters squared, times the offset, which is 2 millimeters squared. Then the contribution from the horizontal piece along the bottom is a BH cubed over 12, which is 24 millimeters times 4 millimeters cubed over 12. And then again, the parallel axis offset is also 2 millimeters, so this is plus the area, 96 millimeters squared, times 2 millimeter offset squared. And the relative size of these contributions, this is 1536, and this is 512, and the result is that Ix is 2048 millimeters to the fourth. For Iy, again we have the two contributions from the vertical parts of the U. That's hb cubed over 12, 12 times 4 cubed over 12, plus the parallel axis offset, again the distance between the local y-axis and the y-axis of the centroid of the shape is 2 plus 12, or 14 millimeters. So this is plus the area of 48 millimeters squared times that 14 millimeters squared. And then for the horizontal member along the bottom, again, its local y-axis is coincident with the y-axis of the centroid of the shape. So there's no parallel axis contribution, and we get just an hb cubed over 12. So 4 times 24 cubed over 12. And the relative contributions here are 18,944 and 4608. And the net result for Iy is 23,552 millimeters to the fourth. In example 3, we have a little bit more complicated problem. We have a precast concrete beam that we're trying to lighten by manufacturing it with 3 identical circular holes. We want the depth h of the cross-section if the area moment of inertia about the horizontal axis through its centroid is to be 4 times larger than the area moment of inertia about the vertical axis through its centroid. Now in this case, most of these dimensions are fixed except for the overall height of the beam. So in this case, it's a little bit easier because we can see where the center of the shape is to start with, and that's going to be right here. Of course, we also have local coordinate axes for each one of these circular cutouts. We can write expressions for Ix and Iy by writing down the expression for the rectangular section and then subtracting an appropriate expression representing the circular cutouts. For Ix, we have for the overall rectangle bh cubed over 12. Again, we'll omit the dimensions, but everything will be understood to be in inches. B is 10 inches. Our height is h. And we can subtract off first the center circle. That is relatively straightforward because its center is coincident with the center of the whole section. And we had previously for Ix that this was equal to pi over 4 times the radius of the circle raised to the 4th power, and that's 2 inches to the 4th. Now we also have two contributions from the upper and lower holes, and those are going to have a parallel axis contribution. Again, the area moments about their centers are pi over 4, 2 to the 4th, but now we're adding the area, which is pi r squared, times the distance between parallel x-axes, which is 6 inches, squared. For Iy, all of the y-axes are coincident with the y-axis for the whole cross-section, so we don't have any parallel axis contribution. We just have hb cubed over 12, and we're subtracting 3 equal area moments, which again are pi over 4 times the radius to the 4th. Our job here is to find h such that Ix is 4 times Iy. Now we can reduce the complexity of those expressions for Ix and Iy a little bit, and if we do that, what we end up with for Ix is 10 h cubed over 12 minus 300 pi. That has to equal 4 times Iy, which is 1,000 h over 12 minus 12 pi. We can rearrange this first as 10 h cubed over 12 minus 252 pi equals 4,000 h over 12. Then multiplying through by 12, h cubed minus 3024 pi equals 4,000 h. And finally, dividing by 10 and rearranging, we have h cubed minus 400h minus 302.4 pi equals 0. And I'll make reference to this cubic expression as we continue to explore our solution. Because this is a cubic expression, we'll get 3 roots. The roots could be positive or negative, real or imaginary, but a physically meaningful solution must be both positive and sufficiently large for the answer to make sense. Given the fixed positions in the cross-section, the height h can be no smaller than the vertical distance from the top of the upper hole to the bottom of the lower hole. For the dimensions given in the figure, this distance is 16 inches. If you have a graphing calculator, you could plot the cubic polynomial as a function of position starting at h equals 16 inches and extending to sufficiently large h so that you can see where it goes through 0. The present slide shows the result over the interval 16 to 24 inches, and we see a solution occurs in the vicinity of h equals 21.1 inches. To confirm this, you could plug h equals 21.1 inch back into the cubic polynomial and verify that the right-hand side is 0, or more precisely, that the cubic yields a number that's really small relative to the vertical scale in the plot. Alternatively, you could use a software package to find the roots of the cubic. A solution is shown here using Mathematica. Again, we need to be aware that there are many instances in physical science where governing equations yield more mathematical solutions than there are physical solutions, so we want to be sure to choose the appropriate value. Since there are more significant figures shown in this result, you may want to plug this number, 21.0958, back into the cubic equation to verify the residual is even closer to 0 than it is with 21.1 inches. Because we often use the parallel axis theorem in conjunction with composite shapes, the centroidal values of Ix and Iy are tabulated for many common shapes on the inside back cover of your book. A couple of points bear repeating. The parallel axis theorem can only be used with the centroidal values of area moments as the reference moment on the right-hand side. This is also emphasized in a column labeled Common Pitfall in the margin in section 10.2. Also, be aware of the location of a shaped centroid relative to the xy coordinate system of interest, which may be very different from the xy coordinate systems in these figures. This is important in defining appropriate distances dx, dy, and d to use in the parallel axis theorem for each shape. If you follow these rules, the composite approach provides a powerful tool for constructing area moments of inertia for a large variety of shapes.